Hey, welcome to Fat Mama Physics! In this video, we're going to talk about scale diagrams and reduction 6.2. And, yes, so this is kind of like, scaling, this is the opposite of scaling up, in opposite of enlargement. This is reductions, basically taking something really big, and to put it on paper, you kind of have to scale it down. I did mention I was gonna do a board game, and I said I promise I'll try to make it short this time, which will be a little hard, but I'll do it. I'll try my best. Okay, so here's the board game. Okay, can you see this? It is called Patch History. It's a fantastic game to play with one or more players. It becomes too militaristic if you're just playing with two people. According to history, that happens a lot, especially in warring nations, when there's not a lot of people to compete with except just the one person, the neighboring country or something. Sorry, I can talk so much about this, but anyways, Patch History is great. The reason why I picked this game is because Patch History pretty much takes kind of a good chunk of history and condenses into a playtime of about 4-ish hours. It's still kind of long, but it's a fun game. It's totally worth 4 hours of playing time. Think I'm crazy? Yes. Imagine you playing your video games. It's the same idea. Okay, so essentially, instead of scaling length, I'm scaling time. I'm scaling time down along pretty much the history of mankind, or a little bit later than that, to the scale of, say, 4 hours. This is not the only game that does that. Another great game is called Through the Ages. It's actually ranked higher than Patch History on Board Game Geek. It is a fantastic game. You can also play that one online on an app as well. But here, let me just turn on my phone just to show you the setup of the game. Okay, so I have the game here. If you didn't see Patch History, okay, so there it is. It looks very nice. You got different kinds of warlords and big people there. So here's a setup. Essentially, this is only one side of the board, and so I have everything here hidden because in the game there's a bidding. There is a bidding phase where you bid for cards, or you bid for these little cards, patches, what we call, to put on your board. So here's your board. You got your resources tracker, and this is your people. You can, depending on what you do in your game, you can get your people to go on these. Oops, I can't pick using my camera. Get these people to go on these trade routes, which then are connected between you and another player. So imagine another player was over here, not a mouse. Then, if I get to the other side, I can decide whether or not I want to make war with him, or just come back, or make peace, or whatever. But the cool thing about this game, which is the patching portion. So this is my patch. It contains resources, and depending on what patches I'm able to bid and win, this is Mosey's. Notice this is near the beginning of time. Then I can patch him directly on here, in which the wastelands I'm able to tuck under my original patch just like this, and or I can use it to cover up whatever is on top, which is kind of stupid because that means I am taking away my resources that I currently own. So for this guy, maybe the best way to patch him would be, I might patch him like this at the beginning of the game, because maybe I can put something over here later, because I have this here as a backup. So I can patch something over this. For example, let's say I have the Colosseum, I can patch that over my wasteland just like that. Okay, so that's kind of the idea of patching. It's you create your little patch, and why it's called Patch History. And there's 3 stages in the game. Stage 1, you notice there are different people and wonders, big historical figures, so heroes, so Alexander the Great, you can see him, Moses, so wonders include pyramids of Giza, Cyrus the Great, Colosseum. So this is kind of like near the earlier time in history. Then you go into the mid-age, the middle years, Taj Mahal, William Shakespeare, Chichen Itza. I always like to say Chichen Itza for some reason. And then here, later on, you have people like Nelson Mandela, stealth aircraft, Gandhi, Red Cross Apollo. This is just example, street wall. So, I mean, on the back side of these cards, there are resources, so you can decide which one side you want to patch. But yes, it is very artsy. It's a very colorful, and this is like the passage of time. Oh yes, and if you wanted to know the other game I mentioned, which is Through the Ages, you can find it on an app on your phone. Here I have Through the Ages. Here you can see I have some other stuff on here as well. Ha ha ha. So Through the Ages, and that's what it looks like. Not going to show you my username, but anyways, it looks really cool. The You can play that on your phone, which is also kind of showing the passage of time and condensing it, scaling it down to, say, maybe how many hours of playing time you have. All right, so here's the game of Patch History. There's a bunch of components in the box I haven't taken out, and hopefully you enjoyed that. So I'm gonna pack the game away. Okay, so that was the game, Patch History. Love it. I took less time, 4 minutes, which is half the time. Hopefully it wasn't that long. But anyways, so let's get on to what we're doing today, which is reductions. With reductions, you essentially will have a small scale factor, because imagine before you had a larger copy of or the image, but this time you have your original diagram is going to be a lot greater. And that reminds me of something. I forgot to show you this. This is the scale of the universe, and I'm not going to play the music. It might be a little distracting. Plus, sorry, baby's sleeping. Baby is sleeping. So, righty, so I'm going to quickly show you what this looks like. Now, a Boeing 747 plane is really large in real life. It is scaled down to paper size for us to see. So in actual reality, this is 10 to the power of 1.5. So this is about 100-ish meters. 100-ish meters. So scaling up, meaning I'm going to be, as I'm zooming out, notice these structures are getting bigger and bigger and bigger, but on my piece of paper, on my screen, it shows a little small diagram. So this is what it means to reduce something really big to something very small on the page. Okay, so I'm reducing. Ooh, neutron star already. Damn. Okay, so Grand Canyon, we're getting to getting to very large countries and planets. Hey, look at some of Jupiter planets. I forgot which ones they're called. I know Io is one. Maybe the Titan? Is that one of Jupiter's planets? Oh, this is Saturn's only large moon. Well, I should know my solar system better than that. Callisto. Galilean moons. Yeah, sorry, did I say moons? So yeah, moons of Jupiter. Europa. I think Europa should be. Anyways, I know Io is definitely one. Do they not mention it? Okay, sorry. Okay, keep going. Hey, USA is pretty big. Okay, so we keep going. And we're taking something very big and scaling it to something small on a piece of paper. Okay? So the original size is bigger. That's what I want to say. The original is bigger. And okay, so lots of planets and lots of stars now. Oh, now we're talking about galaxies. No, sorry, that was a nebula. Oh, a light year. Hoo-hoo, light years. And these are we getting to, these are galaxies now. Star constellations, galaxies. Okay. Ooh, did you see that? Yeah, that's Yoda meter. Oh, okay. Ooh, oof, that's if I blow up to 10 to the power of 27 zeros. That's a lot. So that's the observable universe. This is estimated size of the universe. Did you know our observable universe is shrinking? Because how fast our universe is expanding at an accelerated rate. Interesting space stuff. So make sure you stay tuned for Science 10. But guess what? If you want all this to make sense, better do good at Math 9. For Science 10, we get to talk about stuff like the universe, space, all that cool stuff. So that is what it looks like to reduce something very big, which comes back to my original point. Your original object is going to be bigger than whatever's on your page. So imagine a fraction. If you have something very big on top and something very small on the... Did I say that opposite way? If you have something very big on the bottom and something very small on the top, you're going to get a fraction. You're going to get a number that is smaller than 1. Here you go. Reduction means you have a scale factor that is less than 1. Bring this mic closer to me. All right, so then here below I have a diagram. Notice that these guys are not going to scale very well on your piece of paper, so I just made some numbers up, okay? But they should scale very accordingly. So this is 0.3 repeated, if you can't see that very well. Okay, so let's do this question. We're going to try to find the scale factor here. Imagine this pin. I love math. It could be whatever. I love science. I love board games. It's a pin imagine in real life, that's the size. But on a sheet of paper, we don't want to waste that much ink, so we're going to scale it down to this size. So this is the original. This is the original. This is the copy. Okay, so then we're going to do some math here. To find the scale factor, we're going to figure out how each of these corresponding lengths scale down. For our, what is this? This is the diameter. Okay, so the diameter of my pin, the copy is 2 centimeters. Okay, my original copy is 3 centimeters. 2 over 3, that's going to give me 0.6 repeated for my scale factor. Notice it is less than 1. For the heart, I have, let's see, for the copy, I have 0.3 repeated. Okay, and then for the original, I have 0.5. So if I do on my calculator 0.3333 divided by 0.5, I'm going to get 0.00006 repeated, which is exactly the same as the top. These corresponding lengths are proportional, therefore scale factor for this whole thing is 0.6 repeated, or if you wanted to write it as a fraction, it's probably better this way. 2 over 3 is the fraction for that. Okay, so now we have this one, example 2. This is a diagram. We did a similar example in the previous video for scaling up, but this time we're going to scale down to something smaller. The scale factor is 0.5, meaning everything is going to be halved when you draw this on your 1 centimeter grid, meaning every box represents 1 centimeter length and width. So maybe a good time to pause the video to try this question out. Okay, I will do this one for us, so I will go over it. Okay, so we're going to take our scale. So we have each of these numbers here is the original. So we want to scale this down, meaning we need to take each of these, we got to multiply by 0.5 to give us the smaller sized length. So 2 times 0.5, which is half of 2 centimeters, is 1 centimeter. 4 times a half, or halving it's going to give me 2 centimeters. 6 centimeters halving it's going to give me 3 centimeters. These are my corresponding lengths. So now I think that is everything on our sheet of paper. So we are going to draw this on our diagram. And I'm going to, it doesn't look like I'm going to need a lot of space, because notice my whole length here, the vertical drop is only 6 centimeters, which then if I scale it down by half, it's only going to be 3 centimeters. 3 centimeters is not very much, so it's kind of just this much here. Right there, this is 3 centimeters, which corresponds to this length, since it's a scale down. Okay, so let's go across. Go across 6 centimeters, which scales down to 3 centimeters. 3 centimeters across. Okay. And then we're going to go down by 2 centimeters. 2 centimeters scales to 1 centimeter, so only 1 down. We're going to go 4 centimeters back the way we came from, which scales down to 2 centimeters. So that's 2 boxes. 1, 2. We go 2 centimeters down, which scales down to 1 centimeter. Bam. Then we copy this shape here. We can pretty much complete it. But I'm just going to write all of these values here for your reference. That's 1 centimeter. And this goes down by 2 centimeters, which scales to, whoopsies, not that one. 2 centimeters scales down to 1 centimeter. So that's this guy. And last but not least, 6 centimeters across, which scales down to 3 centimeters. All right. Okay. It wasn't too bad, was it? All right. Okay, so guess what? I'm gonna end the video here for examples. Please tune in for more examples in the next part of this video, 6.2 Part 2. Thank you for watching. See you next time on Fan Mama Physics, signing out.